Hello everyone. We're going to be looking at one more problem in moments. This is moments about a point as well, but we're going to be solving this problem in 3D. And usually, when you have a moment problem in 3D, the easiest way of solving such a problem is by employing the vector approach. So in this problem, we will employ the vector approach first in solving the problem, and then we will eventually see, okay, if we use the scalar approach, how good or how bad the problem is, or how well the results are manipulated to a certain extent. Alright, so this is still moments about a point in 3D though. And we will first draw the problem, then we will set up useful information in the problem, and then we will choose a particular approach to handle this problem. Alright, so here is a problem. I have the x, y and z coordinate system. So the z-axis, and then I have the x-axis and then the y-axis right there. I'm going to extend the y-axis onto the other side. Right, so this is going to be the positive x, the positive y, and the positive z. And now there are two cables which are connected as follows. The cables are drawn in red color. So there's one cable which runs from the point A to a point B, which is on the xy plane, on the positive x and negative y directions on the xy plane. So here is that particular cable. And then there is another cable that runs from the same point A to a different point C, as I will be showing here. So this is the point C. This is of course not drawn to scale, as you would have guessed by now in most of the problems that we solve in class. So I have, so this is point A, then this is point B, and then here is point C. And since we have cables are always going to be in a state of tension, which means that along each of the cables there is a certain force that exists. These cables are two different cables. Of course, they are joined together at the point A, or connected at the same point A. Now the force along the cable AB is 350 pounds. And I'm going to draw that in blue. Right, so this force is given as 350 pounds in magnitude, and then the force along the cable AC is equal to 500 pounds in magnitude. So that's 500 pounds. Then the location of points B and C are given to us. Point B is at a distance of 3 feet along the positive x direction. It is at a distance of 2 feet along the negative y direction. And it is sitting on the xy plane. Point C here is at a distance of 8 feet from the x-axis. Of course, as you can quite clearly see, this is not drawn to scale. This is at a distance of 8 feet, and the point A is raised above the xy plane by a height of 6 feet. Alright, so I'm going to draw a line parallel to the y-axis from there. And then the height of point A raised above the xy plane is 6 feet. Let's call the origin of the coordinate system as the point O. And what is the problem asking us to solve for? The problem wants us to find the resultant moment about the point O due to these two forces along cables AB and cable AC. So find resultant moment vector about the point O due to the forces shown. Alright, so once again to recap the problem, I have the xyz coordinate system, positive x, positive y and positive z. This is the negative y direction. Then the problem is having a couple of forces which are acting from point A to point B and from point A to point C, 350 pounds in magnitude and 500 pounds in magnitude. And then we also have the dimensions of these points given to us. Point B is at a distance of 3 feet along the positive x, it's at a distance of 2 feet along the negative y. Point C, not drawn to scale, is at a distance of 8 feet along the positive y, and the point A is raised up by a height of 6 feet along the xy plane. Right, so here is the xy plane, and then the point A is raised up. Alright, so we will first employ the vector approach for this problem, and then we will later on see if we can tackle the same problem using the scalar approach. Okay. For the vector approach, I'm going to very briefly draw the problem once again so that we have an idea of where these points are located. So here is the XYZ coordinate system. And then I have these forces which are acting. I'm going to extend the y direction along the negative y. Right, so this is x, this is y, and this is z. So one force acting this way. This is the point A, this is the point B. I'm going to call this as F A B, and then I have one more force acting from point A to point C, and I'm going to call that force as FAC. And FAC has a magnitude of 500 pounds, and FAB has a magnitude of 350 pounds. And here is the point C, here is the point O, the origin, and we have some distances which were given to us in the previous page. Distance of point B along the x-axis was 3 feet, and along the y-axis was 2 feet in the negative y direction, and this distance here is 3 feet, and then point C was at a distance of 8 feet along the positive y direction, and then point A was raised up by a height of 6 feet. So the first thing I typically do in Cartesian 3D problems is I write the location of these points, right? So point O started the origin. This is going to be 0, 0, 0 feet. Then point A is a fairly easy one. There is only a z distance, so 0, 0 and 6 feet. Then I have point B. This at a distance of 3 feet along the positive x, 2 feet along negative y, and 0 along the z. And then point C is a point on the y-axis, so this is going to be 0, plus 8, and 0, so many feet. And then the next step is to write each of the forces as a vector. Now you see that the force FAB is acting from point A to point B, which means the unit vector along its line of action is the same as that from point A to point B. So the unit vector here is UAB. And you see for the point A to C, the force FAC has a unit vector which is going to be UAC. And so we can write FAB is the magnitude times its unit vector, and then I can do the same thing. FAC is its magnitude times its unit vector. And the basic idea is I need to find the magnitudes, I need to find the unit vectors by finding the position vectors and the distances. Magnitudes are already known to us. FAB is 350 pounds, FAC is 500 pounds. Alright. So with these distances found out and the magnitudes known to me, I'll just rewrite the coordinates of the points from before. So point O, 0, 0, 0. Point A was 0, 0, and then 6. Point B was 3, minus 2, and then 0. And then C was 0, 8, and then 0 feet. Alright, so let's first write out the forces as vectors. So the force FAB is its magnitude, which was 350 pounds, times the unit vector from point A to point B, which means that I look at the coordinates of the point B minus the coordinates of the point A, which will give me the position vector by its magnitude. So this is 350 times the coordinates of the last point minus the first point. Point B is the last point, so this is 3 minus 0, so 3i, minus 2 minus 0 minus 2j, 0 minus 6 or minus 6k. So 3i minus 2j minus 6k divided by square root of the sum of the squares of 3 square, 2 square, 6 square, which is 7. And so if I simplify all of these, FAB, I get to be the following. So this is going to be 150i minus 100j minus 300k, so many pounds. Right, so this is one of our next steps. Then I do the same thing for the force FAC. Force is its magnitude times the unit vector, which is the position vector, by the magnitude of the position vector from A to C. Last point is C, first point is A, so coordinates of C minus A. So this is 500 times coordinates of C minus A, 0 minus 0, so that's 0i, 8 minus 0, that's 8j, 0 minus 6 or minus 6k, divided by square root of the sum of the squares of 8 square, 6 square and 0 square, which is going to be 100. Square root is 10, and so FAC is going to be 0i plus 400j minus 300k, so many pounds. So I have both the forces FAB and FAC found out here. So that means pretty much half the work required for this problem is already done. I'm going to rewrite the forces. Now we're going to look at the moment caused by each of the forces about the point of interest, which is the point O for us. So very briefly, look at the figure here. I have the coordinate system drawn. I have the negative y-axis. Here is the point O. Force starting from point A to point B. This is the point O, and then I have force from point A to point C. And FAB, so this is positive X, positive Y, and positive Z. And then FAB, freshly found out, was 150I minus 100J minus 300K, so many pounds. And FAC was 0I plus 400J minus 300K, so many pounds. Now I need to find the moment of the force FAB about the point O. So here is the force FAB. I'm going to draw these in a different color. So force FAB, and here is the force FAC. Moment of a force about a point, right? So moment of the force FAB about the point O is going to be the cross product of the position vector from the point of interest to any point on the line of action of the force with the force itself. Okay, so here is the line of action of the force, it's AB, which means that I can either consider position vector from the point O to the point B or the point O to the point A. Right, so this could be one of my position vectors, or OB, or all the way here. That could also be one of my position vectors, which I'm going to call as ROA. Right, so this is going to be ROB cross FAB is the same as ROA cross FAB. Because all I need is a position vector from the point of interest, which is point O, to any point on the line of action of the force FAB, which is either point B or point A. I do the same thing. Moment about point O due to the force FAC is the position vector from the point of interest, which is point O, to any point on the line of action of the force, which means that it could be ROC cross to the force or it could be ROA crossed with the force, because A is also a point on the line of action of the force FAC. Right. So this point has to be really clear. I can either take this choice or I can take that choice, because in both these choices the position vector is always from the point of interest to any point on the line of action of the force, as we have seen in lectures. And the same idea here, I can either take this choice or that choice, and you see that it's always from the point of interest to any point on the line of action of the force crossed to the force vector itself. Right. So here are our choices. So MO about the point O due to the force FAB is ROB crossed with FAB, or ROA crossed with FAB. My second one, FAC, is ROC or ROA cross FAC. And you see that I can take the choice ROA cross FAB, ROA cross FAC, I can add them up and I get the resultant moment. Right, so MO resultant is MO due to the force FAB plus MO due to the force FAC, and this is going to be ROA cross FAB plus ROA cross FAC. You can consider the other two choices as well, they are equally valid. The reason I'm choosing this is because ROA is a common factor. A cross B plus A cross C is A cross B plus C, which means that my resultant moment is going to be ROA cross FAB plus FAC. All I have to do is compute FAB plus FAC, and then I have to take the cross product of the position vector with that, and then I'm done with this problem. Alright, so let's do that. To find out ROA, I need the coordinates of O and the coordinates of A. Those are fairly easy. We already know them from before, 0, 0 and 0 feet. Coordinates of point A are 0, 0 and 6 feet, which means that ROA is the coordinates of A minus O, so this is 0i, 0j, 6k, do not forget the units, so many feet. FAB plus FAC, this is going to be 150i minus 100j minus 300k plus nothing in the I, 400j, 300k, and this is equal to 150i plus 300j minus 600k, so many pounds. So this is going to be FAB plus FAC. Resultant moment is the cross product of the position vector and the resultant force here, and so you see MO resultant, I'm going to look at it from the determinant, first row I, J, K, second row of the determinant is going to be the position vector here, which is 0, 0 and 6. Third row of the determinant is going to be the vector here, the force vector that we computed by adding up these two forces, so that's going to be 150, 300 and then minus 600. Computing the moment here by putting the alternating plus and minus signs, this is going to be plus I times 0 times minus 600 minus 6 times 300, so that's minus 6 times 300, and then I have a minus j times the product of 0 times minus 600 is 0, minus 6 times 150, so that's minus 6 times 150, plus k times 0 times 300, 0 times 150, that's one big 0 there. Alright, so what did we do? We found out ROA, position vector here, then the sum of FAB, FAC gives me the resultant force vector here. The resultant moment is the cross product of the position vector and the force vector here. First row the unit vectors ijk. Second row, the position vectors, populate them. Third row, populated by members of the force vector here. Do not forget there is a negative 600 here, and so we have taken that into account. Alright, so computing the answer, we're going to see, gives us the following. So MO resultant is going to be something in the I direction, something in the J direction, and once you compute the answer, it's going to be 1800 I and then 900 J, so many pound-feet. And if you want the magnitude of the resultant vector is the square root of the sum of the squares of the individual components, so this is 2012.5 pound-feet. So this is going to be the magnitude of the resultant, and this is the end of the vector approach. The basic idea in the vector approach being moment is the cross product of the position vector times the force vector is the cross product of the position vector cross to the force vector. Position vector is taken from point of interest to any point on the line of action of the force.